Aditya sir is here.
Yes, sir. Yes, sir. I can listen.
Okay. Welcome, sir.
Thank you. Welcome. Yes, sir.
Uh, Dear participants, we have a wonderful personality, Dr. Aditya Nigam, with us. Let me give a brief introduction. Dr. Aditya Nigam has received his master's, MTech, and doctoral PhD degrees from Indian Institutes of Technology, Kanpur in 2009 and 2014, respectively. Presently, he is working as an assistant professor at IIT Mandi, Himachal Pradesh, in the School of Computing and Electrical Engineering, SCEE. He has joined this school during August 2014 as a teaching fellow. His research areas include deep learning, biometrics, medical image processing and its analysis, image processing, computer vision, and machine learning. Currently, Dr. Aditya has many externally funded projects worth several crores in hand related to his research area. He has published several research papers in various reputed national and international journals and also attended and presented papers in more than 50 international conferences. Today, Dr. Aditya is with us and will deliver his talk on deep convolution neural network. Just for a lighter moment, I tell you that Dr. Aditya is very interested in the poetry, Urdu and Hindi. So I have two couplets for his welcome. हमने बड़े खुलूस से गोशे सजाए हैं, मेहमान बन के आप जो ऑनलाइन आए हैं, अपने एहसास का अब क्या जिक्र करूं आपसे मैं, आप आए गोया हर सिमत खुशी आई है. With these words, I welcome you, sir, in this FDP program organized at Zakir Hussain College, AMU. And I hope that uh, all the participants will be benefited by your valuable talk.
Thank you very much, sir. And yes, I'm also very happy to, thank you very much, first of all, to Samad, sir, as well as AMU for giving me this opportunity again. I have visited multiple times AMU. And as sir has, read this couplet, it's anyways being expected that if you are talking with learned persons as well as from AMU, then definitely certain things like this need to be coming from. I'm really happy to listen to them, and yes, I'm interested in Urdu poetry very well. Yes, thank you very much. And next, I guess 2 hours are being given to me, and we will talk
Yes,
about deep learning and convolutional neural networks. Yes, sir.
sure, sir.
Okay, so I'm stopping my video and going to start sharing my screen. Yes, let us see. Okay, I assume that you all can see my screen, right?
Yes, sir, it is visible.
It is visible. Good. And Samad sir, can you please tell me that these our participants, they are only allowed to write on the chat, I guess.
Yes, they are allowed to write on the chat, of course.
Okay, but I cannot directly communicate to them. Mean that they cannot use your microphone or other thing.
No.
Okay,
They,
okay,
they
fine.
can type on the chat only.
Type on the chat. Fine, I will manage. Okay, sir. Thank you very much. Starting with this, my name is Aditya Nigam, as sir has said, and it was nice to listen an eminent speaker before me, he was talking about neural networks, and the thing is that I'm also going to start from there. And in the journey of 1.5 hour, maybe closing to two, we'll try to somehow cover up certain things so that you all can understand what this actual fuzz about deep neural networks, why it is better than the traditional neural networks. Because anyways, it's a neural network, it's a different type of neural network. What's the difference between this neural network and the whatever you just have seen, that artificial neural network in which we are having the fully connected network. So starting from the fully connected, I assume that it's already being understood and clear to everyone how these fully connected networks are being working. I'm going to show you a very top level overview of fully connected network very fast. I'll be slightly fast here. Yes, so you are going to have an image like this. A 28 by 28 pixel. This is just an MNIST set of image. MNIST is actually a data set, very small data set right now, but at some point of time, it was being considered as one of the biggest, challenge on computer vision. And what does it say? Just have handwritten digits like this. This is essentially a three, and then somebody will write three like this, and then somebody will write three like this, and somebody will write one like this, or somebody will write two like this, and they have cut all these things, reshaped it into a 28 by 28 size two-dimensional matrix. And how many classes are there? It's actually a classification problem in which you are having handwritten digits starting from 0 to 9, these 10 digits, and so many different variation of this: thick, thin, big, small, rotated, dilated, all possibles of the variations which are being there. And then they have something like 60,000 or 70,000 handwritten digits. Each of them is actually either 1, 0, 1, 2, 3, 4, belonging to these 10 classes. And what was supposed is that if you have an image like this, you train your network some way, so that if I show you these 28 by 28 pixels, can you really tell me that what is its actual class? Given this problem, first I will tell that how this simple neural network, or if I say the fully connected neural network works, what it tries to see. That's a top level intuition, and then from there I will tell you that what are the issues related to that, and from there we will move into the CNN neural network. Fine. So your network need to see this and say that, okay, it is this. And then you are going to have all different types of threes, and it has to see and say that, okay, this is 3 and this is 5 and they are not equal. So you need to understand also that if it is 3 and if it is 5, both of these things are not equal. But essentially your network is seeing image like this. Certain places it is high, certain places it is low, and the low regions are actually black and the other regions are white. And looking these 28 by 28 values, 28 cross 28 values, it need to somehow say that this is 3. Yes, so this is a fully connected network. 28 by 28 is actually 784, which essentially means that I take this all images rows and take first row, place it over here, the second row, the third row, the fourth row, and the fifth row. That's called as the flattening. This is called as the flattening. So I flatten my image, and this is my first layer, that is called as the input layer. My last layer is, of course, is going to have how many classes? 10 classes. And each of the neuron, which is actually over here, it is nothing but going to give you that. After seeing this input, what is going to be the output? What's the output probability distribution that I can say, which essentially means that this value is going to tell that with what probability given input belongs to 1, with what probability the given input belongs to 4, with what probability the given input belongs to 7, and so on. So this is your input layer, this is your output layer. In between these layers, they are actually being called as the hidden layer. And why it is called as fully connected? Because if you take any hidden layer neuron, any neuron over here is actually being connected to each and every one. If you take any neuron over here, it's going to be connected to each and every one. What does that mean? It means that this neuron, if it is connected to each and every, then what is the number of weights that a single neuron is possessing? Single neuron is having 784 weights because it is connected to 784 different entities. And for each and every entity, it actually needs to learn weight. So basically, for each and every neuron, I have actually got 784 things. Then the second neuron, again the 784 things. The third neuron, then again I'm having a 784 things, and so on. So for each and every neuron, I'm having 784 things over here. And now suppose that this is like, 100 dimensions, or 100 neurons are here in my one layer. And then my second layer, second hidden layer is also having 100 neurons. Then this each and every neuron is actually connected to each and every one in the previous layer, which means that this guy was having 784 connection. This guy is having only 100 connections because there are only 100 things over here. So here the number of weights are 784 for one neuron, and such I'm having 100 neurons. Here I am having 100 neurons, and for each and every neuron I'm having 100 connections. So these many number of weights. Here it is going to be how many weights? 100 multiplied by 10, because one thing is connected to 100 things, and how many such things? 10 such things. This is the total number of weights that a network need to learn. That what a neuron is actually doing. Neuron is actually having a weight vector, trying to learn this weight vector in such a way so that I can extract a very specific pattern out of the given data. So this neuron actually is trying to ask a question to each and every input that is actually being seen. But how can you ask a question to a new set of values? I can ask a question by weighing them in a very specific way. So I will show you at some point of time that why it can actually be seen as a question. But right now you see that it need to learn that how much amount of importance this guy is having, how much amount of importance this guy is having, how much amount of importance this guy is having. Why? Because I am actually looking for a pattern, some pattern like this. And if you are looking for a very specific pattern, which essentially mean that these pixels are having a very specific type of weights that this guy need to learn. But what is the pattern a neural network is trying, a single neuron is trying to look for, is going to be dependent upon that what you are actually looking for. So if you are looking for one, you are looking that, do I have a pattern like this? Do I have a pattern like this? Which means that suppose that those pixels which are over here, 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 and here, you can understand after flattening, some pixels will be here, some pixels will be here, some pixels will be here, and some will be here. And suppose that this guy is giving high weightage to them, whether they are high or not. So this pixel is essentially looking for a pattern by which you can affirmatively say that this is essentially 1 or 0 or whatever. Yeah, so I have given you a huge amount of understanding. I will just be skipping several slides because the same thing is going to be shown multiple times over here. Yes, if I show you 9, this guy need to say hi. So if I show you an image like this, what these many pixels are going to be there, and how it's going to be unflattening is the thing it's trying to show it over here. Now you see that it was actually initially a video from which I have converted into a slide. So that's why you can see that slowly this flattening is actually happening. And once you have got this flattened vector, so once you have got this flattened vector, this is going to be your input, and then you are going to get your final output like this. These are your hidden layers. What these hidden layers are actually learning, I will be just going to give you the brief overview. So now you can see that 9 will be coming. That's the input values which are going to come. They started to flow inside this with different weights, because this is having different weights. This is having a different set of weights, and depending upon the weight that these guys have got, certain neurons will be getting a high value with respect to this 9. Certain are going to get a low value, and that is going to be dependent upon that whether it's a 9 or a 1 or a 5 or a 6. Depending upon this input, different pixels or different neurons are actually going to have high responses, and the upcoming layers are also trying to somehow being, combine the previous layer output, and at last certain things, if they got click, if you got a circle like this and a line like this, suppose that circle got this will be learned over here, and a line got this got learned over here, and this guy has learned that both of them are high, then this will be actually connected to this neuron by a high weight, so as to say that this value has to be, the given input is actually having something which is related to 9. Yes, the same things are being actually repeated, and I just wanted to show, yes. So what is going to happen is that your neuron or your neural networks, multiple layers are going to see your 9, 8, or 4 in a different way. It actually tries to divide it to multiple components. This is your component number 1, the component number 2. 8 is having two such components, upper loop and a lower loop. 4 is having, something like this and something like this and something like this. So, so instead of determining that whether it's a 9, 8, or 4, individual layers started to see that whether I can somehow find out that there is a pattern like this and a pattern like this. And if I get both of these patterns, I will say that most likely it's going to be a 9. If I get a pattern like this and a pattern like this, most probably I'm going to see a. Or similarly, 3 patterns, if I see like this, it's most probably going to be 4. And then I say that what are the unique patterns out of this? So unique patterns are like this. So my penalty mate layer, this layer, you need to say that whether it is 1, 0, and whatever the, the big picture. Globally, it is 9 or 8 or whatever. The penultimate layer started to see these small components, saying that whether I can see O or 1 or O, upper loop or lower loop or 1 or half line or, vertical line or horizontal line. So this layer is trying to do the thing for you. But what this guy is going to do, then you will say that, sir, the point is that even this is, that whether it's a circle or not, itself is actually a challenging problem. So why can't you divide that thing also? So now you see that this 0 or upper loop can itself be broken down into very small, components like this and this and this. And if you see all of them, then you can probably say that this is a circle. So what does that mean? This means that they are trying to find out the little edges, and they are trying to find out that how these little edges are combined, and whether their combination is going to lead something meaningful or some meaningful numbers, then these individual guys are going to get responses from the previous layer. Yes. So this is something which was very interesting, and I just wanted to show to all of you that individual layers, when see a 9 like this, a structure like this, it will here try to figure out that whether there something like this or not. And these guys are actually trying to say that okay, some in between, smaller components. And if you have more and more layers, these components become much more discretized, and if they become more and more discretized, at some point of time it will become easier for the initial layers to really figure out that these guys, the input that you have seen, whether it is having some useful low level computer vision related features which you further combine in such a way so that your final layer is going to somehow predict that it is out of 0 to 9 which number it is. Yeah, so this is the first part that I was interested to somehow cover. I assume that let us I don't know that what's going to be the um, um, way in which we can ask questions. So if possible, I will say that if you have any questions over here, I can answer, and then I can move into my second part. Yes, so if you have any questions, I am looking for I guess chat box. I guess I need to see in the chat box. You can write. Let me see. Like the yeah, somebody can read if I am not able to see. If there is any question, yes. Why 28 or 20? Why not other? Because that is being fixed. It's actually very small number, small images. Handwritten digits are usually very small, and since they are very small, they have somehow figured out that 28 by 28 was a good number. It was very old data set, but just a toy data set right now, so as to talk about. Others can also, yes, then we can go 24 by 26. Usually we do not go because we wanted to have a square, and several times we wanted to have even images in the form of if I say power of two, power of two. So later they understood that, because the things that I'm going to talk about, you understand that yes, who is going to choose? You need to choose. As a designer, you need to choose that what is going to be the number of layers, number of hidden layers, number of neurons. Everything has to be chosen by you, because you are going to develop this network. Yes. Anyone else? You wanted to know how, so far, how it is that initially it was a trial and error for a good amount of time, and then we understood that there are so many different benchmark publicly available neural networks, and then you started to gain knowledge from them that how these guys have made these things, what are some good practices by which you can generate big networks that can be properly trained and get very good performance. So then you started to use the available networks and gain knowledge from there. Yes, others can also ask. Please feel free to ask questions. If it is interactive, you people are going to, get more. Yes. Anyone else? I am only, why not happy, because I am not able to see this whole thing at once. And that may be due to, yes, sharing some content. That's fine. Okay. Yes, grid view. This is the grid view. Yes. WebEx. I guess this is my WebEx event. Yes. Anyone else? No. If there is no one, yes, somebody has written. Can you discuss the biasness in the image? How to initialize weights? Yeah, biasness in the image is, several. So biasness is not in the image, but it's actually in the in these weights. We are going to have biases. So bias means that if I give you uh, if uh, if I give you a value like 20, whether you are going to be biased towards it and say that yes, I'm going to work, or you will say that 40, then I'm going to work for you, or if I say 80, then you are going to work for you. So that's actually the neuronal bias, which essentially say that after what value this neuron is going to this neuron is going to fire. Somebody said that how to initialize. There are, in upcoming literature, there are so many different ways by which uh, you can somehow by initialize these networks, such as Xavier's initialization or other things. But initially, given these type of networks, they are being initialized using randomized weights. So just give them random weights, and the good thing is that it will work. It will work for you. Someone else has written as well, but I don't know why I'm not able to see all this consolidated. Oh, WebEx, where is this WebEx guy? Yes, you keep on writing if you have questions. This is actually slightly complex. You are sharing, I'm fine. Yes, that I know that I'm sharing it in this way. How can I see? Somebody can read, if possible. I can answer one by one. um,
I think the last question is how to initialize weight. Huh?
Sir, there was one more question in between. After that, how to initialize weight. Somebody has written one more thing.
Random range of weight.
Okay, random range of weight. Yeah. So if he has written that, then yes, that is true. That most of the time we used to. Thank you so much, sir. I request that something is happening because of which I'm not able to see the chat. So if you are there, please. If anyone asks any question, please read it
Yeah,
out.
yeah, sure, sure,
Yeah.
sure.
Okay. Thank you, sir. Thank you. Yes. So fine. Yeah. Randomly weights can be randomly initialized, and most of the time they are being randomly initialized. We are not covering that what are the good ways in which it can be properly initialized, but there is huge amount of research which is being done The point is that if you initialize it in a wrong way, or maybe you're using some random weights, the only thing is that convergence to the best parameter is going to take some time. That is the issue. That's the only issue, let me tell you. Other than that, things are fine. So later you say that, yes, we wanted to convert it in the best possible way. So yes, there are ways by which you can properly initialize. Yes, so I guess that we are okay with this. And now we are going. So first thing is that there is some issue with this type of network. And the issue is that, I wanted to ask, I wanted to know something about a pixel. I wanted to know maybe something about this guy, this pixel I am interested in. If I'm interested in any pixel, how you are going to see that pixel? This pixel will be somewhere over here. And because it is, flattened. So what has happened is that spatial relationship between the pixel is actually being broken down. What does the spatial relationship mean? Spatial relationship means that if there is a pixel over here and it is actually black. Why this is black? Because within this neighborhood several pixels are there, and they are not randomly selected values. They are actually pixels which are within an image, and this pixel is black because that was actually the part of the hair of a person. And why this pixel is black is that because the whole context near itself in the within a particular neighborhood, it was actually like that. And that is the reason this pixel is, having a specific texture and a specific type of color. So the point is that our fully connected network, why they are fully connected? Because each and every pixel over here is being connected to each and every one in the previous layer. So if I say that these neural networks, they perform well, we are fine. But the point is that And the point is that these neural networks are not going to extract the full spatial relationship between the pixels. You cannot extract, because this spatial relationship got broken because of image flattening. How can you see an image as an image? Right now, you are not looking image as an image. You have taken a 2D image, converted into a 1D vector, and you have shown that 1D vector to your network. And because of the fact that it's not able to really see what are what are those pixels which are within a particular neighborhood, this network will not be in a position to really exploit that information. And just because of the fact that you are not able to really understand that spatial relationship, several problems are going to happen. Why an image is an image? Because it's having a huge amount of spatial relationship. What does that mean? See, this pixel and this pixel, they are sharing a particular edge. All the pixels, there are at least hundreds, maybe, not 100, but maybe at least 10 to 15, 20 pixels over here. And all of them are sharing what? They are sharing a very specific edge. And why they are sharing? Because they are within a neighborhood, and there is a spatial relationship. This pixel is having a relationship with this as well as this and this. Why there is a turn over here? Because there is a relationship because of which these turns are going to happen. Who can learn these things in the best possible and the efficient way? And that is one thing that's being understood, that your CNN is the one who can learn this thing. Why? Because then in CNN, we are not going to flatten the image, and we are going to ask 2D question. What does this 2D question mean? How can we ask such 2D questions to anyone? These are the things that we are now going to somehow understand. Yes. So I am going to the next part over here. And this next part is slightly simple, if I say, not very difficult to understand, but those who have done some image processing stuff, they may be able to really understand it fast. Those who are new probably may take some time, but try to understand the intuition behind this. And after this intuition, we will move towards convolutional neural networks. Okay. Yeah, so basics of an image and a convolution. So what is actually an image? We just have seen. What does an image mean? Image means that's actually a two-dimensional array. How many pixels are here? There are 4 by 4. That's a 16 pixels over here. Okay. Given these 16 pixels, what are they? V1, V2, V3, V4, V5, V6, V7, V8, and V16. These are their corresponding gray values. So if I say what is V10, V10 is nothing but the gray value of the third row's second column pixel. Third row, third column, it's having value V11 and so on. This is my image I. So that's why image can actually be seen as a 2D function. Why? Because what's the function? Function will take two values and going to give you a single value out of that. So image is actually a function which will take a x comma y two coordinates, and it is like this, and v7 or the value with respect to that location is you are going to return as an image. An image can actually be seen as a two-dimensional matrix, and in fact can also be said as a function. Okay, fine. Yes, so I don't know that who is calling. Is it Samas sir, can you listen?
Yes, sir.
Yes, sir. Why I keep on, my phone active, because in between some maybe you may call that, okay, sir, your connection is lost. That's why I have to, my
No,
phone
no, you are
on.
continuously audible. There is no
Audible.
issue.
Thank you, sir. Yes, yes, yes. I'm sorry. Sometimes phone will ring because I cannot shut down the phone because that is the only connection apart from this network between me and Samat sir. So I'm not going to take any phone, but it is on.
No, no,
Yes.
it is smoothly running. There is no
Smoothly.
issue.
Thank you, sir. Okay, fine. Yeah, so this is now V6. So this is, some pixel over here, and the corresponding value is V6, and this pixel is over here, and the corresponding value is this one. Yes, so I guess this is also fine. Sometimes it may be that these values V1, V2, V3, V4, and so on, they may be binary, or sometimes it may be, binary will essentially mean only single bit value, which is actually black or white. Gray means that instead of 1 bit per pixel, I'm going to give you, 8 bits. So if I give you 8 bits, using these 8 bits, you can count 0, 0, 0, 0, and all of them are 0, and all of them are 1. So all of them are 0 is essentially 0, and all of them are 1. In binary, they are essentially 255, in fact. Yeah. So that is, the whole gray level spectrum. Now, the point is that that suppose that if I show you an image like this, which is having, whatever the, m cross n size image, and there are having huge amount of pixels out of there. Suppose if I show you an image like this, you just consider this image. Most of the places it's actually black, only few pixels are yellow. What are the places where you feel that your interest is going? You will definitely say that, oh sir, these pixels are not important for me. Yeah, they are not having any information at all most of the time, but these guys are having some information. And what are those? Why they are having information? And these guys are essentially, but some difference is there between them and their neighborhood. Because of this, these guys becomes important. This is 0, this is 0, this is 0, this is 0. Because of that, all of them are not of much use to me. And then I say that this is 0, this is 0, this is 0, and this is some value. And why this is important? Because with respect to its neighborhood, with respect to its context within a particular neighborhood, it is having some difference. It's having some variation. And that is why these guys, these pixels which are over these line, they become important. So if I show you an image like this, in which I'm having x1, x2, x3, x4, and there is a line which is passing like this. And then I show you the x7, x8, and x9, maybe these, and they are also having, a different line. So I'm having two edges, E1 and E2. I have got two edges, E1 and E2. And given these two edges, I am saying that x1, x2, x3, x4, these pixels are important. X5, x6, and x7, they are also important. And why? Because they are over edges. They are high changes. How can you expect? How can you get how much amount of change is being there? That is nothing but the derivative. If there is a change, derivative will be high. What does a derivative mean? Derivative is a very simple thing. F dash of x. What does this f dash of x means? That f of x minus f of x plus h divided by h, and h tending to 0, limit of h tending to 0. But in our case, limit of h cannot tend to 0 but will tend to 1, because that is the minimum. At least you need to move into the next pixel. So h, if it becomes 1, then your derivative becomes fx minus f of x plus 1, and that is your finite differencing. With using this finite differencing, you can figure out at any pixel that whether it is having a difference from its neighborhood, and if there is a good amount of difference, that pixel is having a high derivative. And if that pixel is having a high derivative essentially mean that these pixels are important, these pixels are over certain edges. Okay, we understand that what are the pixels within a given image. What are those pixels which are important? Pixels which are important are those which are having high gradient, high derivative in different. So as I say that gradient or derivative, your next question is going to be that, sir, gradient is always in a direction. Which direction you wanted to take the gradient? And if I say that there are only two direction, one which is x direction, one which is y direction, because it's actually a 2D matrix, two-dimensional things. So two directions in which you can go, this or this, then they get gradient or derivative can actually be in two directions. I say that either you can find out your gradient in this direction. What does that mean? That in this direction, I wanted to know the derivative of this guy. I will take this value and subtract it with this and subtract it with this. So in this direction, if you take subtraction, that is going to give you the horizontal derivative. And in this direction, if you take the gradient, basically take this pixel, subtract it over here or here, that is going to give you the derivative in y direction. Essentially, derivative is going to play an important role. How many derivatives you can compute? You can compute, if your function is two-dimensional, then you can compute two derivatives. If your function is three-dimensional, maybe in x, y, and z, and you are having some curve like this, then you can have a derivative in this direction, you can have a derivative in this direction, and you can have a derivative in z direction as well. Now the point is that we understand that guys which are having high derivatives, they are going to play some important role in figuring out that what these images represent. See, if you wanted to know something about the whole image, that what it is, suppose that 9 is here, suppose that you have got something written like this, and then this pixel you wanted to see that, oh, it's having an edge which is going something like this. How can you know this? You can know this that if this guy is having a gradient, high gradient, and in some directions which are something like this. So if you can somehow figure out that what are those pixels which are having a very specific gradients and high gradients and in certain given directions, then you started to understand that, okay, what are those pixels which are important. And as in my previous slide, I have shown that there are certain neurons which will try to figure out that in input, there are certain pixels which are having a very specific type of direction. And then in the next layer, different pixels which are having different type of direction, they started to combine and combined in such a way so that you started to see that, okay, this pixel is having a direction like this pixel is having a direction like this, and the next layer will see both of them and say that, oh, there is some structure which is having something like this. And now you see that if you keep on adding structures like this, you started to see bigger structures. If you can see the nano structure, then from nano structure the next layer is started to see the micro structure, and then the furthermore next layer is started to see the macro texture. And at last, when you see the whole texture or the whole shape of the image, what is being there, then last layer started to understand that whether it is 9 or 8 or 5 or things like this. Yeah, so as I have said that if you are having an image, you can have two directions, one in X, one in Y. So you can compute directions in both, derivative in both of these directions. And now you can see that if I have a 9 like this and a 7 like this, within this 7, you can see that these guys are having a very specific, these pink guys, they are having a very specific type of gradient direction. And these yellow, green guys are having a different type of direction. And both of these directions, if we understand, then, later layers will somehow understand that, okay, I am having some text, some directions like this, then I'm having some directions like this. Maybe this is going to be 7 for me. Or similarly, you can say that you started to see something like 9. But the point is that who is the one? Is there a way which will, before that, what does this mean? This is, that do we have, a way which will take an image and tell that, okay, what are those pixels which are having gradient in this direction? Okay, do you have a filter or a function which will be something like this, which will take an image like this and tell me that what are those pixels which are having direction, gradient directions like this? So can we have, filters or, derivative, filters that can extract the derivatives in these directions? We understand that why do we require derivatives in these directions? And we understand that if we can get directional derivatives like this, they will be useful. But the point is that how can we extract such thing? And the answer is convolution. And that is why I explained the whole thing, that why do we require these informations? And once we understand these informations, how can we get that? Using our convolutional neural network. But before that, we need to understand what does a convolution mean. So if you if you are able to understand up to this, next 5 minutes I will explain convolution, and you will be in a good understanding of in a position to really understand that what does a convolution mean. Yes, please wait for some time. Okay, yes, I'm waiting. If you have a question, please ask. Sir has said that.
Aditya sir, actually someone was asking for attendance sheet, so I replied to that. Oh,
Okay.
you
Okay,
please
so
continue.
okay, continue. Thank you, sir. Yeah, so now let's talk about this convolution. Oh my God. Yeah, so this convolution, uh, because there is someone who is continuously calling, I'm going to give this phone to someone. Yes, sorry. Yes, for this convolution, let us give that I'm having this image, I'm having this filter. What is this filter? This is my directional filter. I wanted to see that this f of x comma y, which is again going to be a 2D function, can I design a function and come up with an operation that will somehow do this thing for me? What does that mean? Mean that take an image like this this filter and tell me what are those pixels which are having gradients in this direction. Which means that this operation is actually being shown as a convolution operation, and if I have an image like this, apply some filter over that, I am going to get a response, and this response need to be the those pixels which are in this image having a directional derivative as confirmed by this filter. This is the thing that we need to somehow manage and make. Now let us see. I'm having an image like this. It's actually a big image. You assume whatever size I'm cross and I'm just taking a 3 by 3 set of pixels inside this. In fact, I am right now interested in this pixel. I'm only interested in one pixel right now. I wanted to know that this 33 guy, this is having a specific neighborhood of 3 by 3. I wanted to know that, hey, do you have, what is your horizontal derivative? Horizontal derivative means that I will take this and subtract it with this. Yes, as I have said that you take this and subtract it with this, that's your horizontal derivative. Okay, I wanted to know this, that do you have a high horizontal derivative? I wanted to come up with a method that will somehow figure out that whether this guy is having a high horizontal derivative or not. So what I'm going to do is that just take a 3 by 3 matrix like this. This 3 by 3 matrix minus 1, minus 1, minus 1, 1, 1, 1, and 0, 0, and 0. What I am going to do is that I take this and place it over here. What does that mean? I placing minus 1, minus 1, minus 1, 0, 0, 0, and 1, 1, and 1. And then I multiply this with minus 1, this with minus 1, this with minus 1, this with 1, this with 1, and this with 1, and this with 0, 0, and 0. And then if I add all of this is somehow going to give me an approximation that whether this guy was having an edge which was going in this direction, horizontal direction, or not. What is the horizontal and the vertical derivatives, how I can get? Let us see one by one. Is that probably now you can see, may not be able to see, this is minus 1, minus 1, minus 1, 0, 0, 0, and 1, 1, 1. When I multiply this with minus 1, this with minus 1, and this with minus 1, you have got minus 12, minus 22, and minus 6. And these guys become 0. And this becomes 101, 121, and 91, 92. When I add all of them, this is happening over here. That when I'm adding all of these things, first of all, 9 values were here. 9 multiplications has happened. Out of that, these 3 guys becomes 0. This value got subtracted from this value got subtracted from this, and this value got subtracted from this. This is nothing but actually an approximation which is somehow going to tell you that what is the horizontal variation this 33 guy was actually experiencing. Someone can ask a question slightly, if you are not able to understand, I can repeat. If you want to ask a question, please write in your chat box. I'm looking. 1, 2, 3. Please ask. If there is no question, I assume that it's anyways was not very difficult. Kindly repeat, Ashutosh. Okay, Ashutosh. The point is that I wanted to know that whether this guy was having a gradient, horizontal gradient. What I have done, I need to somehow find out the difference in this direction. How can I find out a difference in this direction? Either I can subtract this from this, or I can subtract this from this, or I can subtract this from this, and so on. So what I have chosen is that I am going to subtract this value from this value. But not only in this, within a particular neighborhood. So I will subtract this from this, I will subtract this from this, I will subtract this from this, and add these 3 values. These 3 values got added. And that is actually telling me that whether what is the horizontal derivative of this guy. If within the horizontal direction, not things are being changing. Right now you see that the values are different. 101 and 12, big difference. 121 and 22, big difference. 92 and 6, big difference. There is huge amount of difference, and because of this, differences that we are actually having, this value becomes high, and that is actually telling that yes, there is some derivative in this direction. If you can somehow figure out that, so that is how you have got that. I have got that using this filter. I take this filter and apply it over an image like this. Right. So this is -1, -1, -1, 0, 0, 0, and 1, 1, 1. And yes, that is the thing which is happening. Similarly, the things are actually happening over here. Here you can see that we are talking about -1, -1, -1, 0, 0, 0, and 1, 1, 1. And now here you can see that one filter was -1, -1, -1 over here, and 1, 1, 1 over here, and the next filter is -1, -1, and 1, 1, 1 over here. Similarly, you see that here these values are negative, these values are positive, and that is going to tell that we are going to talk about the diagonal derivative. This is actually going to give us a diagonal derivative. This is going to give us a different type of derivative. This is going to give us a different type of derivative. And if I place each and every value 1, 1, 1, 1, 1, 1, 1, 1, 1, this is nothing but doing the averaging. What does that mean? If my filter is 1, 1, 1, 1, 1, 1, and 1, 1, 1, all these values are 1, 9 values 1, this is going to give me the averaged out feature for this guy, which is nothing but adding all of them, which is nothing but the averaging of the image. I have got an average pixel value for this guy. Instead of 128, I will be having the addition of all of them. And this averaging is going to introduce blurred. It may also happen that there was some noisy pixel, black noisy pixel, and that got, with respect to its neighborhood, when it's got averaged out, this value will actually be changed and converted into the average, and that noise will actually be removed by applying the average filter. So this is essentially the filtering. What we used to do, we take an image, okay, we take a filter, fine, we take this filter and place it over the image one by one. First I place it over here, this is with respect to this guy, then I slightly move it to my left, and that is with respect to this guy, and then I move into the left, and that is with respect to this guy, and then I move into a left, and then I get value for this guy, and keep on doing. And once I'm finished over here, I will move and do it for this, like this, and then I do it for this. So what we are doing, we are taking a filter. Let me show it if it is here. Yes, I will take, this is my image, I take a filter, place it one by one, first over here, then this, then this, then this, then this, then this, and so on. And when I am done in one direction, then I keep on applying, just moving one pixel downwards, and then I keep on applying third, fourth, fifth, sixth, so on, and then you are done in this direction, and then you keep on doing. So in this way, what we are doing, we are filtering each and every pixel. And what this guy is doing, this filter is asking a very specific question, that whether you have a vertical edge, whether you have a diagonal edge, whether you have a horizontal edge. And the response for each and every pixel, after multiplying those values, neighborhood pixel values, by that filter values and adding them, you are actually getting the responses. And these responses that you have got, they are actually telling that what is its x derivative or y derivative or diagonal derivative or what. And what we used to do, we take image, we take a single filter and keep on asking the same question to each and every guy. And the response map that you are going to get for each and every pixel, that is essentially the answers that you have got for each and every pixel when the that filter has been applied over that. And the question that is asked by the filter, what is the output or the response for what is your response for that particular filter. It's been well shown probably again over here, that this is your source image, this is a filter, I take this filter, place it over here, and then, somehow I multiply this. So this 4 got multiplied by this got multiplied by this got multiplied by this. The 9 multiplications, then you add all of them and a single value is coming over here. And then you switch it up to here. And then you switch it to here. I'm sorry. Then you switch it to here. And then you keep on switching it in that way. And you are going to get values for this and this and this and this and this. And this is going to be the response map that you are getting. That is your final response. Again, you can see it over here, some nice animation. So single values you are able to see. This is essentially showing you that if you apply a horizontal edges, only those pixels, some images being there, you can see that the responses that you are getting mostly are something like this. So you can see horizontal edges when you apply horizontal filter over an image. Or you may get a vertical direction edges when you apply over the same image. If you apply 2 different edge directions, you are going to get sometimes pixels which are having these direction edges. Here you are having pixels which are in this direction having high values, and merging both of these guys, you can see horizontal as well as vertical components. Till now, nothing deep learning, just only that, this was the thing. It's being done for all the time in computer, the traditional machine learning. And let me also tell you the difference between the traditional computer vision and machine learning things as well as the deep learning is that I am having an image. I guess you all can see I'm having an image. Okay, given this image, I wanted to figure out that whether there is a cat or a dog or something. So I need to find out from this image, I need to figure out the features. Features means that what are those important things over which if I uh, concentrate, I am going to somehow get the best possible answer. So given an image, to get the feature, these are feature extraction. I'm sorry, my bad handwriting. And that's, let me write it properly. Feature extraction. Now, this feature extraction algorithms, there are so many different types of computer vision and image processing based feature algorithms. So your image I finally got converted into a vector of features x1, x2, x3, and xn. And then these features are being given to your classifier. Your classifier is not going to take the image. Instead, it is going to take the image or these signatures. Once you have got these features, this classifier is going to take these features and going to do maybe binary or tertiary or whatever 10 class classification. It's doing the classification for you. So if I say that what is here, this is actually image processing. This is computer vision. So image processing and computer vision, two different types of techniques and available subjects. In fact, signal processing was also being there. So use all the possible techniques over there. At some point of time, this was actually the research area so as to get the best possible features. So you handcraft the features. You say that, oh, you want to differentiate between A and B, then these type of filters you need to be looking for. Then somebody will say, oh, you want to differentiate between cat and a dog, then these type of filters you need to look for. Who is going to make these filters for you? You yourself as a researcher need to read a lot of computer vision and image processing techniques and define the best possible filter that can be useful for the type of classification you are looking for. So you handcrafted, manually handcrafted. And then this classifier will come from here. It becomes like bishops and duda heart, machine learning text. They will just say that I'm not bothered about these x1, x2, x3, and x4 and xn. You just give me the features over which I need to train my classifier. If these features are good, my classification will also be fine. My classification will also be good. So in Bishop and Duda Hart, you just say the data is given to me, capital X. What is that? That's actually a vector. How you have got this vector, they never ever talk about. They just say that give me the data. Data means the features. Once I got my features, I will train my classifier. What classifier? Bayesian. What classifier? Hidden Markov. What classifier? Support vector. What classifier? Gaussian mixture. What classifier? Maybe you want to do clustering, then k-mean clustering. Whatever algorithm that you wanted to train, you train. There are so many different algorithms. They will say that, okay, this algorithm is better than that algorithm, assuming features x1 to xn remains to be the same. So you are having two different domains. One is computer vision and image processing type of field from which you need to work and come up with the best possible feature extraction techniques. And the other one is the machine learning technique that is saying that if you give me the best possible features and then apply the best possible classifier, then you are going to get the best possible results. Now, if you do not get good results, then classifier person will say that, oh, I am not getting the best possible features. When you go and ask the feature man, he will say that, oh, I am giving the best possible feature. Maybe your classifier is not yet tweaked. And this keep on happening. This conversation between these two guys keep on happening to and fro. And you keep on getting your things better and better. But here comes the deep learning system. Deep learning will say that I am having feature extraction plus classification, and both of them are combined inside my single unit, and that is actually the convolutional neural networks, and that I'm going to show, in which the initial few layers, or if I say that the convolutional layers, which are essentially learning the convolutional filters, that 2D filters I just have shown, -1, -1, -1, 0, 0, 0, 1, 1, 1. Who is going to tell you these filters? They are going to be learned. By whom? By network. Who is going to let me learn? Using different types of optimizations, back propagation, losses are there, and your network is going to learn that what has to be the best possible filter. If I know that filter, I apply it over the image, and that's going to, giving me the best possible feature. So the initial few layers will be learned as a feature extractor network. And when you have got a good feature, then after that you apply a neural network classifier. The neural network is having its own classifier. So the initial CNN layers are going to be used to extract the best possible feature, and classifier is going to be used to finally do the final level classification in between whatever the classes that you have. Yes, this is the second part is done, and after that I will start my third part. Before that, I assume that all of you understood what does convolution mean. If you have questions, you can ask about the convolution. About convolution. After that, we are going to use these convolutions to understand how these convolutional neural network actually learn and works. Yes, convolutions. Any questions? Till now, no one is saying. Let me count for 5. 1, 2, 3. Full convolution. Full convolution. Can you explain what you want to ask? Convolution means that you take a filter, place it over each and every pixel, and get the response for the full image. So given an image, example you explained. As the fully connected networks are there, I just have explained the previous thing, that will be used as the classifier, and then we will be applying convolutions. So first we will be having convolutional neural networks, and then we will be having last layers are going to be fully connected networks. Maybe in the next 10 to 15 minutes, we'll explain Number of classifier. Output image by applying. Please, how can you convert a negative to zero? A negative to zero. Why I wanted to convert things from negative? Anyways, image is not going to be negative. Image is always going to be some value between 0 and 255. So value will not be negative, but in between features are going to be negative. And if we are going to have a negative features over that, we are going to apply a ReLU type of activation function. So after every convolution layer, we will apply a activation function. This activation function is nothing but some type of non-linear functionality, and a ReLU is something one such function which will take any value. If it is negative, it will make it 0. If it is positive, value remains to be the same. Sir, can you read in between questions, because they were very fast? I was not able to read. Okay, sir. Gaurav Gupta is saying okay. Samad sir, can you listen? Abdus,
Yes.
Yes, sir. Any question? Yes, sir.
Output image by applying filter. Please explain the problem.
Output image by applying the filter is that I have an image. I have just have shown that I am going to have an image. I am having a filter. Image can be m cross n. Filter can be 3 cross 3 or 5 cross 5, or depending upon that what is the neighborhood in which you wanted to apply your filter. I take an image m cross n. I take a filter 3 by 3. Place it over here. You will get a value or a response for this guy. Place it over here in the response map. And then you take the next thing, place it over here in the response map. So your response map, this value is the output of the corresponding pixel when we have applied the actual filter over this pixel in the original image. And I have got an output over here, then I will apply, and then I will get an output over here, then I apply, and then I get an output over here. So that's the response generation. For each and every pixel, I apply the same filter. And when I apply the same filter, I am going to get different answers. Why? Because each and every pixel is having a different answer to the same question. Because the question is something like that: what is your horizontal gradient? What is your vertical gradient? And each and every one is having a different answer. Yes, this is done. Other one, sir? Is there anyone else?
There is no question in the chat
No
box.
question. Chat box. Okay, sir. Thank you. So I assume that once we understand this convolution, let me go and pose the problem now in a different way. My fourth part, not now, my fourth part. Now, let me see. Is this the fourth, or it has to be the third one? I have just covered this. It has to be which one? Yes, this is the thing. Let me go on top first of all. Designing that the case is steady. Fine. Week 1, part 2, part 3. Okay, yes, this is the one. Fine. Convolutional neural networks. Publicly available, several good YouTube tutorials and other things are being there. Let me start it in a very different way. So this filtering, what is going to happen of an image is nothing but a visual interview of an image. It's a completely different thing. What does a visual interview mean? We have understood that each and every filter is essentially a question that you can ask. If I show you -1, -1, -1, 0, 0, 0, and 1, 1, 1, this is the question. Whether you have an horizontal edge, whether you have a vertical edge, whether you have any directional edge, you just ask a question. And that question can actually be designed in a 2D filter. Okay. Once we understood this, what is that question that need to be asked? Then you will say that, sir, that depends upon that what is your task. What does that mean? It means that I am going to select. So all of you are my students. You wanted to apply to my lab, and wanted to be a PhD student. So if I wanted to select whether this guy can be a good PhD student or a bad PhD student, or should I select him or not select him, I need to ask questions. So when I know that what is the objective, I will be asking questions. So you are yourself a data, or you can assume yourself as an image. And as an image, you are having huge amount of information. I am not going to look each and everything what is there in you. Being a student, having an infinite amount of data inside you. What is that infinite amount of data? Let me tell you. Your name is there, your father's name is there, your the place where you are living, how much marks you have got in 10th, how much marks you have got in 12th, how much marks you have got in 8th, 9th, what is your sister's name, what is your brother's name, what is your mother's name. All this information, there is infinite, each and every data is having infinite amount of information. My image, if I say it's having m cross n pixels, and each pixel is having one value associated to it. So if my image is of size 100 by 100, then I am actually having 10,000 values. Are these 10,000 values really important to me? I said no. Why? Because see, I am interested in some very interesting, important thing. Similarly, if I take you as a data and wanted to ask a question, I need to design a question in such a way so that if I ask you, you give me an answer by which discrimination started to happen, which is discrimination between whom? Discrimination between the data points D1, D2, D3, D4. Discrimination amongst the students started to happen, which is going to be helpful for me to understand who to select, who to reject. Now, talk about these questions. These questions are completely tied to what is going to be the objective. If I'm going to select you for my PhD student, I need to ask, okay, what's the name? If I ask what is your gender, most of the time it is not useful. If I ask where you are living, most of the time it is not very useful. What is your father's name? It's not required. But it may be that what is your 12th marks. It may be from where you have done your BTech. It may be whether you know Python. It may be how good you are in linear algebra, how good you are in probability, how good are you in some subject. It may be, do you have some prior experience of machine learning? Do you know convolutional neural network? Up to what extent you know what is convolution? Have you done a course on Coursera? Now, if I take the same question, copy paste, and take them to another interview, and the objective is different. Now I'm going to select you for my cricket team. Now I'm going to select you for my cricket team, and that is going to be a men's cricket team. And if it is men's cricket team, my first question need to be that, hey, you need to be men. Now this gender is important. I need to ask that what is your gender, and then I will say that, oh, if it's female, no, if it is male, yes. Why? Because it's a male cricket team. And then I should not be asking what is your 12th percentage, because it's useless for me right now. I need to now ask, can you tell me whether you are a batsman or a bowler? Can you bat? At what level you have played cricket? Are you a wicket keeper? Are you a pace bowler? Are you a spinner? What type of cricketer you are? Now, you understand these questions are completely changed. What are these questions and what is this data? Data is D1, D2, D3, D4. Right now, being interviewing you are the data. Usually, this data is going to be images. Image number 1, image number 2, image number 3, image number 4. And these images I'm having sometimes cat, sometimes dog. I wanted to see them and figure out that whether there is a cat or there is a dog. Understood? Now it comes that if I figure out that what is my problem, images are my data. If I know that what is my question, what's my problem, what has to be my questions? And my questions are these two-dimensional filters. Okay. Basically, you wanted to know, basically also being written over here, what is your directional gradient? Do you belong to a line like this or this or this? Because they are low level questions. If I understand, do you have a left line, right line, medium line, thick line, thin line? Hey, do you have a pattern like this or this? How can I ask these questions? We just have seen that we can have a K by K filter that can understand that whether you have a line like this or a line like this or a line like this or a plus like this or a cross like this. Do you belong to a blob, red blob, green blob, yellow blob, blue blob? All these things can be well embedded inside a two-dimensional filter. And when I take that filter and apply it over an image, what does that mean? That is a question that I asked to that particular pixel. Now let me show you here. What does this visual interview mean? Visual interview means that I'm having a pixel like this over this pixel. I apply filter number 1, filter number 2, and filter number 3. You are going to get, so basically, oh, for whole image, if you apply filter number 1, you will get the response map, full response map. For each and every pixel, you have got a response map like this. For this image, if you apply another filter, another response map. And for this third filter, third response map. What is this? This is nothing but the answer given by this guy to this filter. Hey, do you have a edge like this? He will say yes or no, depending upon whatever the value that you have got. You can understand that whether he has said yes or no. Then you apply second filter, and then you will get another response for the same pixels, answer to this guy. This filter is asking same guy another question, and the response is actually over here. And the response of the same pixel to my third pixel is over here. So I take this image, apply different filters. That is actually the visual interview. Okay, what are the questions of the interview? Question number 1, question number 2, question number 3. What are the outputs? So if I take this pixel, only this pixel, its responses are this, and this. Its responses are this, and this. Okay, yes. With this, let us start our problem. Our problem is that I wanted to make a CNN. We need to design a CNN classification network, which will take an X or an O and differentiate between them. So if it's an X, it has to say that it's an X. If it is an O, it will say that yes, it's an O. If it is an X or if it is an O, it's going to differentiate between them. How can I design such a network? How can I design such a network is, so by the way, these images and other things, they are also being taken from here. So you can see that this is available, some small lecture by which this guy was trying to explain something. From that I have adapted and added things that I wanted to add out on top of that. Yes, so given a CNN network, differentiating between X and O is the thing that is your final objective, but it's not a simple problem, because axis can be this, small x, big X, rotated X, dilated X, maybe shrinked X, or same with O. And all of these things when go in, X has to be X and O has to be O. So these variations really make this problem very, very difficult to solve. Why? Because if I show you an image like this, and if I show you an image like this, can you say that both of them are same or different? And your question and your answer will be, sir, both of them are same or different. It is actually not very clear. In fact, these are the red places where both of them were completely different. And how many pixels are there? 14 such pixels where the things are completely different out of 64. And it's actually a big number. To 10 to 20% error is actually being there. And if you allow this much amount of error, you cannot say that both of these things are same. So essentially you wanted to say that most of the things are actually different. So both of these things are, in fact, this guy and this guy, both of them are different. But you understand that your classification is X or O. This is not very similar to this, but this guy is completely dissimilar to O. And that is why you may say that, okay, this is an X. But how can we figure out, how can we do this? So let us see that there were so many places where agreement was not being there between these two images, but let us see that yes, they were very similar. Why? Because this area is completely same as this area. This region is completely same as this region. This region is completely same as this region. This region is completely same as this region. This region is completely same as this. In fact, all the components are equivalent, exactly similar, but part-wise they are exactly matching. But we were looking the whole image as a complete global structure. And if you see things in a complete global structure, you may find it really difficult when things are slightly distorted. They started to change the structure. And then you wanted to see that how much component wise they are getting similarity. But your normal algorithms will not allow you, but CNN can help you to see the image in parts. How? So let us see that there is someone who is telling you that, see, these are the three questions you need to ask. Who is going to tell you? That is the thing I have said, that these are the three filters. These are the three questions. These questions are directly coming from what is your objective, which was actually differentiating between X and O's. You wanted to differentiate between whether it's an X or it is an O. When you can differentiate between both of these things, you can say that my classification is done. But what question somebody need to ask? It has not to be predefined, but need to be learned. So right now, as an oracle, I am telling you that you can apply these filters and things are going to work for you. And then you understand that why I am saying, because by this filter, you can find out whether there is an X that you may find out in between this type of structure, or you wanted to know something like this or something like this. So these are the three things if you somehow get. So that's why here, I'm sorry, that is why you are actually looking for something here or here or here. So these three filters are more than enough and sufficient for you to learn or differentiate between X and O. So these are the useful questions. Who is going to tell you? By back propagation, your neural network, convolutional neural network by its own need to learn, because these 9 values of this pixel, they will be randomly initialized. These 9 values of these pixels need to be randomly initialized, and this will be also randomly initialized. After this random initialization, you keep on applying over your incoming data and see that when I apply this, what is the output that I'm going to get. If you are getting a wrong output, you need to tweak your parameters or these filters in such a way so that they started to move in the best possible and the correct direction. And then you keep on doing until and unless over the training data you started to get good and good results. And once you started to get good results, they are bound to come very close to these filters. It is going to be learned. Right now, I'm going to be assuming that suppose that somebody has given you these three filters, how we are going to use these three filters? Very simple. The way in which we are going to apply this is I'm getting an image like this. Over that, I apply this filter, then I apply this filter, and then I apply this filter. If I take this image, apply this filter, I am going to get a response map number 1. For each and every pixel over here or here or here, I have applied this, then this, then this, then this, and keep on doing. So you will be getting a response map like this. So to your image I, right? You have got three filters, right? And then you have got response map R1, R2, and R3. These are your three response maps. How does they look like? But before that, how can we get this response map? That's the convolution I just have shown in my previous section, that I take this. If I take this filter, take this image, and take this filter and apply it over here, 9 multiplications are going to happen. These are those 9 values. They are being normalized by 9, and you will get a single value, this, that is being placed it over here. That is the output of this pixel, which is being placed over here. That is with respect to this filter. This filter placed it over here, you have got an output like this. That is only for one pixel, and then you do it for this and this and this and this and this and this and this, and keep on doing. You will get output response map for each and every pixel for any given filter. That is a response map. Now, this is your input, this is your filter, this is your response map. You can see that these guys are slightly higher than the other guys. Why? Because when this filter being placed over here, you have got a high response because it's having an edge like this, and it was asking the same question. If you apply this filter, or the plus your cross filter over here, you may not get a high response. But these guys are having high responses. Only here these guys are having high responses. Then I take this, apply this filter, apply this filter, and apply this filter. I will get 3 response maps. I stack all of them, and these response maps are actually going to be useful for me. Okay, once you have got a response map, once we guys have got a response map like this, what does this mean? This means that original image, when I apply a filter, what is the output that I have got? This is being placed over here. Over that, I am applying a nonlinear activation function that is called as ReLU. What is this ReLU? And the way in which it's actually being shown like this. If it is negative, it becomes 0. If it is positive, it remains y equal to x. What does that mean? All the negative values become 0. Positive value remains to be the same. That's the non-active, non-linear activation that we have added over here. That was the first step. The second step is that once I have got an image, over that I choose certain filters. Basically, I'm learning certain filters. I apply those filters. I have got a response. Over that response map, I apply an activation function, and then I have got a feature. Over that, I started to do a pooling. This is called as the max pooling. What is our max pooling? Our max pooling is that I will take an image. I take 2 by 2, then next 2 by 2, then next 2 by 2, then next 2 by 2. And instead of having all of them in my feature, I will choose the one which has given me the maximum response. You need to understand that we are not doing averaging of these features. Features cannot be averaged, because if you average out the feature, the important information that you must have got with respect to any pixel is actually averaged out, and everything got averaged, then you will not be getting any information at all out of the image. So from 4 to 1, this is most of the time 4 to 1. When I say that you have got 2 by 2, 4 things, we wanted to get a single thing. Instead of doing the averaging, we need to choose the one which is performing the best. It is just like that. Over the whole image, I divided into 2 by 2 grids, basically multiple groups, and out of that group I am choosing the guy which is the best one, and this is my reduced feature. Why this guy is taken? Because see, I wanted to know something what is happening inside my image. I have asked my one question to each and every one. I wanted to know how well, what is the final consensus. Can I say that there is an X? Can I say that there is an O? But given these many values, it is slightly difficult. I wanted to reduce the size, so I taken 2 by 2, and the one who was the best, it's been coming over here. Nobody is best. Whatever the one which is having the maximum value will be coming over here. In this way, the most important pixels information got retained it over here. So I'm retaining the pixels which are having the maximum responses. The responses which are high, they got retained. By the way, when we apply 2x2 pooling, 2x2 pooling, when we apply this 2 by 2 pooling over any image, you can understand that if the size is m and n, what is going to be the size? If I apply a 2 by 2 pooling and stride is just, if I place it over here, next time I'm going to place it over here, which means that stride is 2. 2 by 2 is this, the next 2 by 2 is this, and the next 2 by 2 is this, the next 2 by 2 is this, and if there is nothing, you assume that they are 0. The next 2 by 2 is this, the next 2 by 2 is this. Then what will happen that if your image size is m cross n, and if you apply a 2 by 2 pooling in this way, your dimensionality becomes m by 2 and n by 2. M by 2 and n by 2. Now, suppose that your image size initially was 512 by 512. Then you apply certain filters. You will get certain responses. Then you apply activation function. You have got the activated responses. And then you apply pooling, max pooling, and your activated responses got shrinked. And if it is 2 by 2, then the height and width got 256 by 256. And then you again apply certain filters. That's a convolutional layer. Then you apply ReLU activation. And then you again apply pooling. And then your filters, your size becomes 128 by 128. So after first, if your input is 512 by 512, after first pooling, it will become 256 by 256. Then it becomes 128 by 128. After next pooling, it will become 64 by 64. Then it becomes 32 by 32. At some point of time, you understand that my feature vector size becomes very small. Since it becomes small, now it is not going to have much amount of, now it's not going to have much amount of spatial relationship. So if it is not having much amount of spatial relationship, so if it's not going to have much amount of spatial relationship, what we expect, then we can open it. The way in which we have opened in our fully connected network. What are these response maps in between that we are getting? What are these response maps? These are the features that we are getting. And if you understand the way I have said, our CNN network initially apply convolutional layers, then pooling, then convolutional layers, then pooling. What is actually doing? It is trying to extract the best possible features that it can get. Keep on extracting multiple set of features, features which are good, features which are important, features which are meaningful. And once you have got this best set of features, at some point of time, you understand that after 3, 4, 5 pooling, your image becomes 4 by 4. Your image or your feature become maybe 8 by 8, maybe 16 by 16. And then you say that no, now over that I do not want it to apply any convolutional layer. I do not want it to see it as a 2D matrix. I do not want it to ask now 2D questions. Why? Because you have got an aggregated information about the image, because each time when you apply pooling, when you apply filter, you get local information because it's over a local patches. When you apply pooling, it started to aggregate things within a particular neighborhood, and after multiple pooling, you started to get maximum values of certain things, because one max. Then next time when you are doing max, so assume it in such a way so that this whole thing was your old village, and then first pooling was being done when you was at 10th class. Then next pooling was being done when you was in 12th class. Then the next pooling done when you clear JE. And when you are at IIT, what you see is that all of them are good. Out of that also certain guys are performing well, and because they are the max of the max of the max of the max and so on. So only at the last layer, only those guys are being there who are graduating from IIT and then doing MTech and then doing PhD from Stanford and CMU. Then you say that, oh, these guys are 5 guys are there. And what are those 5 guys? These are those 5 pixels which are the best important pixels. Just by seeing them, you can say that what was written in that image. And you wanted to show those 5 things or 8 things or small number of things to your classifier. Now these 5 things or 8 things are actually the final features that you have got. Over that you wanted to train your classifier. Your classifier is going to be a fully connected network. What's going to be a fully connected network is something like this. This is your input image. Then you apply convolution. Then you apply ReLU. Then you again apply convolution. Then you apply ReLU. Then you apply pooling. If your image is very big, you wanted to apply pooling many times and very early. If your image is already very small, suppose that your image size is 8 by 8. If your image size is 8 by 8, if I do pooling, 2 by 2 pooling, what is going to be the size? What is going to be the size? Please write in the chat box. If it is 8 by 8, and if I apply a 2 by 2 pooling, what is going to be the dimensions of my output? Please write in the chat box. Write in the chat box. I'm not going to, move forward. You need to write in the chat box. My image size is 8 by 8. My image size is 8 by 8. My pooling is 2 by 2. What is going to be my output? In the chat box, can you write? मैं नहीं आगे बढ़ूंगा इससे, मैं बहुत देर से अकेले पढ़ा रहा हूँ. Please come up. It's very simple. It is 8 by 8 is my image. Over that, I am going to apply a pooling. Pooling of size 2 by 2. अगर मैं 2 by 2 की pooling, if I am taking that 2 by 2 pooling over that with a stride of 2, what is going to be the output? I just have explained. What is going to, yes, Gaurav Gupta, it's not going to be 2 by 2. Please attempt it again. 4 by 4 is the correct thing. Yes, Guru Nathan, please, you guys need to say. Otherwise, I feel that where I'm teaching, last around 1.45 hours, we are along with us. You people are along with us. 4 by 4, Anupama Gupta. Others also need to write. Even if you are listening, you need to write 4 by 4. You need to write. Otherwise, I assume I'm teaching to bots. You need to write 4 by 4. Jaldi. Yes. Now even you can see this. Let us understand few more things. We have some time. That's why I'm spending 8 by 8. Fine. I apply a convolution filter 3 by 3 over this 8 by 8. I'm applying a 3 by 3 filter. Sir, it will. Yes, Pranav. Thank you, Pranav. It is 8 by 8. And please be ready. I'm going to ask things. Or uske bina I'm not going to be carrying forward. 8 by 8 is my image size. If you have copy pen, take out your copy pen. Over this 8 by 8, I am going to apply a filter 3 by 3. I am going to get one response. I am having 8 such filters. How many? 8 such filters. What is going to be the output size? What is going to be, first of all, the output dimensions after this convolution? 8 by 8, I'm having a filter whose size is 3 by 3. And how many filters I'm applying? I'm applying 8 filters. How many responses I'm going to get? How many responses I am going to get? Bataiye. You need to write.
Sir, you are not audible. Are you there?
I'm there. I'm giving them time.
Okay,
I
okay.
want all of them to be interactive.
Sure,
They,
sure.
yes, sir, please write. 8 by 8, 3 by 3 filter. How many filters? 8 such filters. If I apply 8 such filters, how many responses I am going to get? You need to write on chat box. See, the size is 8 by 8. I'm applying 8 filters. How many responses you are going to get? Are you going to get 1 response? Are you going to get 2 response? Are you going to get 3 response? If I apply 8 filters, then how many response? Why Manak base was 4? Why we will get 4 responses? If I have 1 image, if I have 1 filter, then 1 response. Yes, Anupma Gupta. 1 image, 1 filter, then 1 response. 1 image, 8 filter, then 8 response. Yes, that's correct. 1 image, 8 filter, then 8 response. If you are having 8 response, they are being stacked one after another. This is response number 1, response number 2, response number 3, response. How many? 8 such responses. What is going to be the depth? 8 is the depth. What is going to be the spatial dimension? Till now, no pooling has been done. Till now, no pooling has been done. That is why 8 by 8 is going to be the output dimension and 8 such responses. Is that clear? You need to write yes or no. You people need to write yes or no. Yes, Menak. Yes, that's true. Others also need to write yes. Yes. You write no, I will explain 20 more times. Yes. Yes. Thank you. Thank you. I guess that now you all get. Hala. Got it. Good. Good. Got it, sir. Ashutosh Shukla. 8 cross 8, 3 by 3 filters, and 8 such filters. Because no pooling has been done till now, you are getting 8 by 8 by 8. That this is my first 8 by 8. I'm sorry. Yes. That means that this is my first 8 by 8, second 8 by 8, third 8 by 8, fourth 8 by 8, and this is 8, this is 8, and this is 8. That is why it is 8 by 8 by 8. Okay, fine. Over this, now slightly tricky, but very, very important thing. Over this, now this is the what is the input to this guy? Input to this guy is 8 by 8 by 8 volume. Yes. Over this convolution, the second convolution, let me write also the second convolution. This was the first convolution. Over the second, when I'm applying the second convolution, how many filters I'm applying? 16 filters I'm applying. Where it is written? Written over here. First thing, if I have a 3 by 3 filter, what is going to be the depth of my 3 by 3 filter? I cannot apply a 3 by 3 filter over a volume. Just to think about, I'm having a volume. What is that? 8 by 8 by 8. Over that, I cannot apply 3 by 3. I need to apply 3 by 3 by 8. That is why we just needed to, we don't write it explicitly because depth of the filter is always equal to the depth of my input. So my second con is going to take input as 8, depth as 8. So my filter, if I say 3 by 3, it is actually 3 by 3 by 8. If it is 3 by 3 by 8, how many filters I'm applying? I'm applying 16 filters. How many output I'm going to get? I'm going to get 16 output. What is going to be the output of this convolution? Is it clear? It is going to be 8 by 8 by 16. Again, you people need to write yes or no. It need to be 8 by 8 by 16. Yes, Mainak Viswas is the only one who is saying yes. Guru Nathan has said yes. Same two, three guys. Ash, Antusha, yes. Ashutosh, yes. More persons need to say yes. Only 5 guys till now. Pranab, 6. Pranab 6, Pranab 6, 7, Dr. Garima 7, 7, 7 guys, 8, Sukhpreet 8, 8, 8, only 8. I don't know how many guys are listening to me. Samad sir, how many participants? I assume that we are having good number of participants. 10 guys have said yes. Out of that, 10 are saying yes. Okay, fine. Now with this, I move forward and apply ReLU over that. You all know that ReLU do what? ReLU will take the things, negative things become 0, positive things become the same. And then I apply pooling. Again 2 by 2 pooling. 2 by 2 pooling, the stride of 2. Size becomes this. I assume this is okay. Understand very important thing. The pooling is only going to reduce the spatial dimension of my filter. You can see that the depth remains to be the same. So after pooling, depth is not changed, but the spatial dimensions are changed. And they are being reduced, they are being tweaked, changed depending upon the tooling. Most of the time 2 by 2 with a stride of 2 is being applied, which essentially make any feature vector height and width reduced to its half. Yeah, so you have started with 8 cross 8. Then your feature dimension become 8 by 8 by 8. And then again, your feature dimension becomes 8 by 8 by 16. And then your feature dimension becomes 4 by 4 by 16. Now you see that the spatial dimension got reduced. And your depth is keep on increasing. And then my third convolution. Two such things. Then the output is going to be of size 4 cross 4 cross 32. Important thing is that here this will also be 30. I'm sorry, this will be 16, because the depth of my filter and the depth of my input is actually matching. This will become 16. Output of my third convolution. Output of my third convolution is 4 by 4 by 32. And yes, I guess that you got the idea how these convolutions are happening. And you understood that at this point of time, my size becomes very small, 2 by 2. Now, over this 2 by 2, after this pooling, over this 2 by 2, why you wanted to apply a convolutional layer? 2D filter, why you wanted to apply? Just open it up and apply fully connected. Yes, the same thing is going to happen over here. Yes, this will become 2 by 2, 2 by 2, and 2 by 2, my last layers. I flatten it up, 4 values, next 4, next 4. This is my flattening, concatenation, and then I apply fully connected. These are the diagrams for the fully connected. Number of fully connected you can apply the way in which just I have shown you previously. in my first section. Now you can apply fully connected, because this is now a classification which is happening. These are the features. Feature engineering has been happened. The four best things out of the multiple asked questions and so on, 444, whatever you have got in my final feature layer is the one which is having the best possible features that you can extract out of your image. I've taken that and apply classification over that. This is my classification layer. Multiple classification layers you can have. That's as I have shown that for them, this is my input and these are actually the hidden layer. And finally, in your last layer, how many neurons are going to be there? Only 2 neurons are going to be there. It's being shown over here. But at last also you are going to have 2 neurons. You can have multiple fully connected. You can have 2 neurons. This is actually the full network for you. If I show it over here your input image is like this: conpool. At some point of time you see that no, not much pooling. To extract, you just flatten them and apply fully connected. Last layer only 2 neurons. Why? Because you just wanted to differentiate between X and O. And yes, your network is done. This is your complete network. Then somebody will ask that how many convolutional layers? What is going to be the number of filters in each layer? What is going to be the size? 3 by 3, 5 by 5, 7 by 7? How many fully connected layers? How many pooling layers? Within each and every fully connected, how many neurons? All these things are actually hyperparameters. Need to be designed and set by you. You will ask that how can I set? You need to see the publicly available, so many big networks and literature is available. BGG, AlexNet, then there are ZFNet, Inception, GoogleNet. There are so many different networks which are available. You just go study them, understand why they have introduced that type of concept, why they use 3 by 3, why they use someone else use something else, why they use residual connection, why they use other things, multiple filters like 3 by 3, 5 by 5. All of them are being used so as to get the best possible representation. So why these people are doing this? You need to read that. You need to understand the state of the art technique so as to design a network and taking these clues from the available network. But the bottom line is, to design such a network, hyperparameterization need to be done. What are these hyperparameters? For convolutional layers, what is going to be the activation function? You can apply ReLU, you can apply sigmoid, you can apply so many other tan H and different leaky ReLU and so many things which are being there. So you can apply those things. Number of filters, that 32, 64, whatever, and the size of the filter, 3 by 3, 4 by 4, and whatever. It's usually 3 by 3, 5 by 5, odd number things. You also need to know that how to stride, how much stride in X direction, how much stride in the Y direction. So these are the things that you need to tell for your convolutional layers. For pooling, you need to tell that what is the window size and what is the stride in X and Y, 2 by 2, 4, 3 by 3, 4 by 4, or so on. Most of the time it's being applied as 2 by 2 with a stride of 2 in the X and the Y direction. And then finally, fully connected layers, which is going to be the number of fully connected layers that you wanted to apply, as well as individual layers. For each and every individual layer, how many neurons are going to be there. Yeah, so I'm done. This is your convolutional neural network, the way in which it's actually being running. You can apply it over any possible good amount of data. If you have over that, you just apply. Some very good network names are VGG, which is actually a very small network, only having 20 or 32 or something like this layers, not too many layers. You can train them. Pre-trained weights are also available, which is you just take and try to solve any of your classification problem. Given images, you want to differentiate between cat and dog, you just take this network, pre-trained network, show it a cat and a dog, and it's going to differentiate that, okay, this is a cat and that's a dog. It will differentiate a priori.
Aditya sir, someone is asking about auto encoder.
Oh yes, so autoencoder is something that, let me give you a brief this thing about autoencoder. Just first of all, look up to this within this network. Look up to this, right? So after this, you have got certain set of features. Okay, so let me redraw this thing for you. That if you have got a certain set of features, what you can do is that from this image, I have gone up to this. These are my set of features. Okay. And from this, I started to do upsampling. So here you was doing pooling, which is like 4 to ka 1. And then I can do unpooling, that is actually being called as upsampling, and which is like 1 to ka 4. Here from 4 you have made 1. Here from 1 you can make 4. That's also learnable. So if you can do upsampling from small things like this, or the final feature, you keep on adding more and more and more, and at last it becomes the same size the way as your input. How can you train such a network? You can show I. These are layers, 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 layers. You have got I dash, and your loss is I dash minus I. What you expect? You expect is that whatever I have shown you, can you regenerate the same thing to me? You train your weights in such a way so that if I show you I, you can show me an I out as an output. And if you can do that, what is the utility of such an autoencoder network? Because you anyways you have I, and your network is giving you I dash, and if it's properly being trained, I dash is going to be very similar and equal to I. And what is the utility of such a network? Utility of such a network is that we are not going to use this. We stop it over here. Once it is being trained completely, I take this I and use these features as the best possible features. Why they are the best possible features? Because you just see that using these many small number of features, very small number of features, the whole I can actually be regenerated, which essentially mean that here it has to learn the pooling in such a way so that only the best possible features are here, so that he can regenerate the thing in the best possible way. If it is being learned, the features which are the bottle, these are also called as the bottleneck features. These bottleneck features will be the best one. And you can understand that if the same thing I can actually be generated from these many small number of features, then they must be having all the required information which was being there in this I itself. So it's almost like a feature compression or a feature selection type of thing is happening using autoencoder. Yes. Yeah, so I'm done. My things are done. I'm happy that probably you can write your feedback if you want on the chat box. Thank you, sir. Yes, you can write your feedback if you are, happy. You understand, sir. Whether there is, yes, there is going to be the data loss. Yes, it's going to be definitely data is going to be lost. But do you really want to get all the possible data for doing the discrimination? No. If there is a cat, if there is a cat image, then you do not want it to see each and every pixel. You only wanted to see very free, salient features, and that is why it has to be done. Very informative. Yes, this is good. Let me also give you a very good pointer that there are two things that I wanted to tell you all as well. One is that if you really have more questions and you wanted to read things in much more detail, there is one good publicly available resource, because I was teaching this course for last 5 to 6 years, and once I recorded all the things, all of my lectures on deep learning and its application, CS671, that I used to teach here at IIT Mandi. Everything got recorded, and we have uploaded it on YouTube. You just need to write on YouTube, you need to write deep learning at IIT Mandi. Aditya Nigam ke naam se you are not going to get. You just need to write deep learning at IIT Mandi, and you will get some channel where you can get the playlist in which autoencoders, GANs, variational autoencoder, CNN, RNN, reinforcement learning, transformer, BERT, everything is being covered over there. We used to teach and we record these lectures, because I most of the time use my iPad, and everything got recorded using this iPad, maybe on cloud or somewhere. We just download and upload things over there. So things are being publicly available. I'm out of my time. In just last 1 minute, I'm going to say that if you are having much more interest in these things, at IIT Mandi, one online workshop is going to be conducted very soon on from 3rd of July. If you people are interested, it's a 6-day workshop, public online workshop. If you people are interested, you can join things over there. 6-day core deep learning concept. I am done. Thank you, sir. Sorry for taking 3-4 more minutes.
Thank you, Aditya sir. Very deep insight you have given about the convolution and deep learning and all these. I think that participants have enjoyed a lot as they are giving responses in the chat box. And you rightly say that if pupils are interested, then they can join your workshop that is going to start from 3rd of July next month. With these few words, Aditya sir, I am very thankful to you for accepting my request. And I have not directly communicated to you, but Professor Saiful Islam is there.
Yes, that's true. I'm very happy and I've got this chance. Thank you very much for this opportunity.
And
Yes.
next time, hopefully, whenever this pandemic time went off, we will call you in person in AMU in some other program. I hope so.
Yes, sir. Thank you very much. Thank you very much to you, to AMU, to Saif Bhai, as well as all the our participants. Thank you very much. And this learning is endless. If people are really interested, go and check on the resources publicly available, freely available, and just enjoy the deep learning. It's huge amount of stuff is actually happening in this area.
Exactly,
Yes.
exactly. So for the participants, now this is the time for their lunch break. Please have lunch at your places and assemble again on the same link at 3 p.m. For the third and the last session of today.